Hello, welcome back. Now, in the last video, we talked quite a bit about ionization chambers and how they worked, and I showed you a couple different chamber models and a diagram of each of those. Especially, you'll remember the farmer chamber. That's the bigger one, the 0.6 cc volume ionization chamber that we use for reference dosimetry. And now I'm going to go back and describe in more detail how we actually calculate dose. So you'll remember that I showed you this picture in the last video and talked about cavity theory and just the general concept that we're going to measure a charge and then we're going to go over and get the dose out of it. And so now I'm going to dig into that in a little more detail and show you exactly how that's done and what the factors are that are involved. So here we go. So as we go to do this conversion of charge to dose, you need a recipe or a formula, a protocol that tells you exactly how to do that. So in this video, I'm going to be making reference to the AAPM Task Group 51. It was published in 1999, which goes through in detail how to do this. And then here's a clickable link that you should be able to use to download this. One thing you should be aware of is that there was an addendum published to TG51 in 2014. Here's the link for that. It didn't completely replace the protocol, it just made some minor tweaks and added some data for different ionization chambers based on Monte Carlo calculations, but you should be aware of this update. I'd like to mention a couple things about TG51. Number one, it's not the only dose calibration protocol out there. There are others. There's TRS 398 from the International Atomic Energy Agency. There's something from the Deutsche Industry Norm. It's a German group. And then there's something from the Institute of Physics and Engineering and Medicine, IPEM, which is a UK group, and they have a protocol as well. So what I'm going to show here is TG51, but they're very similar. All these protocols have slightly different nomenclature, but the concepts are similar. Another thing I want to say about TG51 is that it's an update and an improvement to an older AAPM protocol. That's Task Group 21, published in 1983. So I mentioned this because Task Group 21 was a bit harder to understand. TG51 was an improvement because it's simple. It's a very simple recipe. But some of the underlying concepts are actually easier to understand if you're studying this, if you read TG21. It's a little bit heavy sledding, but it's worth looking at. But I'm going to refer mostly to TG51 here. So let's start by looking at the setup for TG51 measurement. So you're going to set up to 100 centimeters to the isocenter and at a depth of 10 centimeters. And you put your, and it's a 10 by 10 field. And then the chamber goes here at that depth. That's where the measurement is made. Now, you're going to measure a charge in that chamber, Q, and then, like I said before, the goal is to convert that to a dose in water. And by the way, for a full TG51 measurement, it's done in water, liquid water, although you can do it more frequently in plastic. So then you get the dose to water is the charge times some calibration factor, N dose in water, NDW. That's how it's called. Okay, so I'm actually gonna change the symbol here. Instead of writing Q for charge, which we normally do, I'm gonna write M. So M is the meter reading on your electrometer. That's the common symbol. And so then the thing is to calibrate this and get the calibration factor, calibrate the chamber, and that's done in a cobalt 60 beam. So you measure the charge in the cobalt beam and then that and you know the dose in water, so that gives you the NDW in a cobalt beam, which we write like this. So this is done in an ADCL, an accredited dosimetry calibration lab, so that it's traceable back to a primary standard. Okay, so the procedure is you send your chamber and your electrometer away to the ADCL. They do this calibration in their cobalt beam where they know the dose to water, and they give you this NDW factor in cobalt. They send it back to you. And you do that at least once every 2 years. All right, so let's look how this might actually work. So you would get your meter reading M, you multiply by this NDW calibration factor, and that should give you the dose in water, right? Actually, no, that is not right. It's close, but the thing is, this is the NDW in a cobalt beam, okay, in a 60 cobalt calibration beam, but your beam is not a cobalt beam up here, it's a LINAC. Let's say it's 6 MV beam or something. So you can't just simply multiply by the calibration factor. So what you really need is to take this NDW calibration factor in cobalt 60 and convert it into some other calibration factor, ND dose in water, NDW, in your LINAC beam. To do that, you apply this KQ factor. That's a quality conversion factor. It's just a number. So if you did that, then the dose to water would be your meter reading times this KQ times your NDW in the cobalt 60 beam. And then you would have your dose to water in the LINAC beam. So let's look at this KQ factor a little closer. Let's look at this plot from TG51. You're seeing here the quality conversion factor, KQ, versus the percent depth dose as measured at 10 centimeters. And you see different lines here. These are different chambers, different models from different vendors, all mostly farmer chambers. You'll see that they each respond differently. And then this is plotted as a function of percent depth dose because there's an energy response for these chambers. So you remember the beams from previous videos, you remember that the beams with a smaller percent depth dose are lower energy, they're softer, and higher percent depth dose are harder beams, like an 18 MV beam, let's say. And so that's the energy spectrum, or we could say the quality of the beam quality. So this is why it's a quality conversion factor. One thing to notice here is the scale. Here you'll see it ranges from 1 to, let's say, 6%. And so mostly these are, relatively small conversion factors of the order of a few percent. But it's important to get it right at this level when you're doing absolute dosimetry very accurately. So let's look how to read this as an example. So in our clinic, we have this beam here at 67% PDD, and you go up and you would read off, you'd find your chamber, and you read off what the KQ factor is. So for example, it might be 0.994, let's say, for this chamber. And then you use that for your formula. Okay, so it's relatively simple protocol to use. All these curves are determined by Monte Carlo calculations. They're very accurate, and somebody's done all that work for you. One thing I'd like to talk about a little bit is this PDD. So it's percent depth dose measured at a depth of 10 centimeters in water, and then it's got the little symbol X next to it. You see that? So what that means is that you're looking at the X-ray component. So you want to filter out the electrons that come from the head, and that's especially important for high energy beams above about 10 MV, because those contribute lots of electrons at shallow depths. And so the way the protocol specifies to do that is you put a lead foil on the head of the machine when you're measuring the percent depth dose, and then you take it off for the rest of the measurements. Alternatively, they have a little formula you can apply and to take out the electron contribution. And the TG51 addendum suggests that you do it that way, with the formula, not with the foil. All right, so now that we understand the KQ factor, I'd like to go back to this formula and look more closely at this M factor. That's the reading on the electrometer of charge. That seems like a simple, straightforward thing. You just plug it in and read it. But there are quite a few corrections that you have to apply to make sure you're getting the right reading from your chamber. All right, so ultimately you want this real reading M, but what you measure is M raw. I'm going to call that's what actually comes out of your electrometer. So you have to correct that with some factors. So first is a temperature pressure correction factor. Then there's an ion collection efficiency factor, P-ion. There's a polarity factor. That's whether you reverse plus or minus voltage. And then finally, there's an electrometer correction factor to the efficiency of the collection in the electrometer. So I'm going to go through each of these in turn. So let's start with this one, the temperature pressure correction factor. And to do that, we're going to look and think about the ideal gas law. So you have some gas inside the chamber, some air, right? And you'll remember the ideal gas law says that pressure times volume is N, that's number of atoms, times R times T. R is just some constant, T is temperature. So if you increase the pressure, you'll increase the number of atoms in the chamber if you keep the volume and the temperature the same. So you have to correct for that. If you have more atoms, you have more charge collected. So we'll correct by some factor for the pressure. So it's some standard, 760, that's millimeters of mercury. That's the standard pressure divided by the pressure. So if you have a higher pressure, the correction factor is going to go down. Now you're also going to have a correction factor for temperature. So let's say for a given pressure, if you let's say decrease the temperature, the number of atoms would have to go up. So you have to correct for that. So here's what this factor looks like. So 273 times temperature divided by 295. Those are the standard temperatures in Kelvin. So this is standard temperature pressure. It's all relative to that. So 22 degrees Celsius or 295 Kelvin and 760 millimeters of mercury or 101.3 kilopascals for the air pressure. And so this equals the temperature pressure correction factor that you always have to apply to your readings. All right, good. So let's go back out here and we're going to move on and look at the next factor on the list here. That's the P-ion, the ionization collection efficiency correction factor. And I'm going to try to explain the physics of this for a minute. So let me draw a parallel plate chamber. It's a little easier to understand. One electrode is at a positive voltage, one is at a negative voltage, or at ground. So let's say it's 300 volts between these. So an electron comes in and it drifts towards the anode. Depending on where it is collected in or starts in the chamber, it could drift all the way across. As it does, it can recombine. So in other words, it combines with other atoms in the chamber, and then it's not collected because it's no longer a charge. And so that reduces the charge that's read if it recombines. So you can make a plot here of the charge that's collected versus the voltage. And at a low voltage, it's not very efficient because there's lots of recombination happening as it drifts slowly. As you increase the voltage, more charge is collected and then it kind of saturates. So this is a typical curve. The size of this effect is pretty small. It's never more than 2% for chambers, but still we have to correct for it to do accurate dosimetry. So the way you correct for it is you pick a voltage here, you measure the charge there, and then you find another voltage here, measure the charge there, and you get that those two values allow you to find P-ion. There's a formula for that in the protocol. All right, so now let's look at these last two factors, P polarity and P electrometer. First, polarity, you'll see the chamber has the positive electrode here and the negative electrode here, but you could flip those and put the negative one here, positive one there, and you would get a different collection efficiency because the chamber is not symmetric with respect to the collection efficiency on those two anodes, or the two electrodes. So that's how you actually do it. When you work through the protocol, you flip the voltage and you measure the collection efficiency difference, and that gives you a polarity correction factor. And then the final factor is P electrometer, and that's relatively straightforward. It just says if you measure a certain charge in your chamber, is that really the charge, or is the electrometer not quite efficient? The correction is typically less than 1%, and the way you get it is you don't do that measurement in the clinic. You instead send the electrometer away to the calibration lab, typically with your chamber, and they tell you what the collection efficiency is. So those are the factors. So here we have all the formula together, and it's meant to be relatively straightforward. You find this raw meter reading, correct by all those factors we just talked about. You multiply by the KQ factor, you multiply by NDW that you get from the calibration lab, and that's your dose to water. Now this is one thing I'd like to mention. This is all measured at 10 centimeters depth in water, right? Specified by the protocol. But the thing is, you typically want to calibrate your machine as dose in centigrade per monitor unit. at a depth of Dmax. That's usually how machines are calibrated. And this is not at Dmax, it's at 10 cm. So we have to somehow convert this measured dose to this dose at Dmax. It's relatively straightforward. We just take the measured dose and divide by the TMR at a depth of 10. And that gives us the dose at Dmax. Recall that as we learned in video 11.1, that the TMR is just the ratio of the dose at some depth to the dose at the depth of Dmax. So that's how you get this formula. Okay, so this is basically it for calibration of photon beams, and there'll be some problems that are important to work through to really understand this deeply. All right, so there you go. Those are the basics of ionization chamber based dose calibrations. And I didn't go over every little detail. There actually is a little bit more. So I'm going to leave you with this reading list to dig into it a little more. In particular, I didn't really spend much time talking about electron beams, and so I'm going to leave it to you to read that, and that'll be in the text. Because most of what I kind of focused on in this video was about photons, because that gives you the basic understanding of what's going on. All right, see you in the next video.